Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff, the most awesome stuff. This is the AAS Journal Author Series, and I am super happy to have Oliver Anagnostou with us today. Hey, Oliver.
Hey, Frank. Nice to meet you. Thanks for having me.
Well, thanks for agreeing to talk about your very lovely APJ article. Definitely caught my eye. Very nice. Oliver, where are you located at?
I'm located in Melbourne, Australia, so right down the very bottom. It's technically summer, but the weather today is leaves a bit to be desired, unfortunately.
Oh, it was a little cool or a little foggy or...
Yeah, just a bit cloudy, a bit cold, a bit rainy.
Okay. It is February 1st of 2023 as we record this. I'm in Phoenix. We are definitely in the winter in the Northern Hemisphere. And so it gets a little chilly in the morning, somewhere around freezing. But then by midday, it's up around 65, 66 Fahrenheit or something like that. So very pleasant. So that's why we get all those Canadian snowbirds coming down to sample that Phoenix. And what's your position there, Oliver?
So I'm a PhD student here, currently in my third year, so still got a bit to go, but it's going well so far. I've been enjoying it.
You got one APJ paper out, so it's very cool. Very cool. Well, I look forward one day to calling you Dr. Oliver. How about that?
I look forward to that too.
Awesome. Cool. And speaking of that, Oliver, what do you like to do for research?
Right. Well, my main research area is looking at the dynamical formation, evolution, and eventual merger of black hole binaries within dense stellar clusters, such as globular clusters.
Cool.
And in service of that, I do a lot of these big n-body simulations of globular clusters. But I like to be quite diverse. So basically, anything involving black holes, I like and would happily do research on, and anything involving stellar dynamics or n-body simulations.
Right.
Those are kind of the three main areas that I'm interested in and doing more of, essentially.
Nice. That's going to be an awesome thesis. And along the way, you got some more awesome papers, which is going to bring us to this first one, which is APJ. It's open access, people. Go grab a copy for free. Repeated mergers of black hole binaries, implications for GW 190521. And Oliver, take us away.
Yep, thanks. So yeah, this work was originally inspired from the 2020 observation by the LIGO-Virgo collaboration of GW 190521, which at the time was the most massive black hole binary merger ever detected through gravitational waves.
Yes.
And this event got everyone in the field very excited, essentially, because since it was so massive, compared to all the mergers that we'd seen up until then, and indeed even since then, it's still essentially an outlier. These component masses of median mass 85 and 66 solar masses were actually potentially within what we know as the upper black hole mass gap. And this mass gap is basically a result of our understanding of stellar evolution and core collapse physics. Not my area of expertise, but some great people have done a lot of work on this. And essentially due to pair instability and pulsation pair instability supernovae, you expect that you would not get any black holes through core collapse above a certain cutoff mass. And this cutoff mass is around 50 solar masses. There's some, give and take depending on how you specifically do the models, but yeah, around 50 solar masses. Now, as I said, at least component mass 1 of GW 190521 is 85 solar masses for the median range. That is clearly above 50 solar masses. So this got everyone thinking, well, how could this have been produced? What's going on here? So there are some possible explanations to how to get such massive black holes. One of them is that our understanding of core collapse physics, and particularly pulsation pair instability supernovae physics, is not complete.
Okay.
One of the ways that this could be is if there's existence of physics beyond the standard model. Um, and this would essentially alter our model for pair instability supernovae.
Mm-hmm.
Um,
Mm-hmm.
but you can actually produce black holes above the mass gap without altering our understanding of core collapse physics. And that's what the focus of my work here is.
Okay. Cool.
So there are a few mechanisms, and the particular focus is looking at dynamical formation within dense stellar environments, such as globular clusters.
Mm-hmm.
So some great people like Sapera and Kremer have done some simulations and found that you can get mergers of stars early on, which produce essentially these weird hypermassive stars with extended envelopes
Okay.
that can collapse and form black holes within the upper mass gap. There are other methods, though, which will be the main focus of today, which is essentially when you have what's known as a hierarchical merger or repeated merger of a black hole. So basically, you have these two black holes, they merge and form what we call a second generation black hole.
Okay.
If that second generation black hole sticks around, it can go on and form a binary and merge again. So that could be what we're seeing here, where this 85 mass, 85 solar mass black hole is actually a result of a previous merger. And that's kind of what we want to investigate with this paper.
Nice.
So unfortunately, though, it's not all sunshine and rainbows. There are quite a few issues with these repeated or hierarchical mergers.
Okay.
The main one being this so-called gravitational recoil. So gravitational recoil is essentially a result of when you get these binary mergers, if the gravitational waves, which carry away energy and momentum, if those gravitational waves are not emitted symmetrically, then there'll be some net linear momentum flux. So
right.
if the gravitational waves are preferentially flinging that way, then you're going to get your second generation merger black hole flinging that way.
Yes.
And some great research using numerical relativity has found that you can get these recoil velocities in excess of 1,000 kilometers per second, which is well above the escape velocity of any globular cluster, and indeed even galaxies as well. That's not good for forming second repeated mergers.
Right.
Yeah, because we want to retain these black holes. So that was a big thing that we needed to look at for this work.
Okay.
But yeah, so in this paper, we're using a set of direct n-body simulations, a set of 58 n-body simulations that simulate globular clusters. Basically, what we do is we're using a code called n-body 6, and you set some initial conditions, and then you click play, and then you hope it runs to completion. And also you hope that in that time, the stars go through stellar evolution, and then hopefully form some black holes. They hopefully form some binaries, and they hopefully merge. So we start with no black holes. We start with just stars drawn from a saltpeter IMF.
Okay.
And then we let them evolve through stellar evolution package SSE and BSE, which were developed by Jarrett Hurley. And then, we get the black holes and then see what happens. Now, with these set of 58 direct n-body simulations, which was presented in the previous paper of mine, we found that in one specific simulation, we got a repeated merger of seven black hole mergers in a row, where the same black hole would form again and then merge again and then merge and so on.
Wow. Okay.
And for the purposes of this paper, I'll refer to that black hole as Snowball for obvious reasons.
Okay.
And yeah, so this was unique in our set of simulations. So we had plenty of other black hole mergers in our 58, but this one was unique in that forming the 7 mergers. And yeah, so I won't go into detail about the specific initial conditions. I'll let the listeners read the paper themselves. But the one thing I will mention is that natal kicks. So these are quite important. So when stars go supernovae, it's kind of similar to the recall in that if the supernova is ejected asymmetrically, then you get some momentum flux in a direction, and the resulting black hole gets kicked in a direction. The base version of M-Body 6 does not include prescriptions for fallback, mass fallback onto the black holes, which alter the nodal kicks.
Yep.
But so to account and to get like a similar number that you would expect based on those fallback prescriptions, we essentially just apply lower natal kicks, which are adjusted based on the velocity dispersion of our specific model. So it's not quite equivalent, but we get approximately the same number of black holes retained as you would for this through fallback descriptions. And now the other important thing to talk about is gravitational recoil, as I discussed previously. So again, N-Body 6 does not include gravitational recoil in the base version. But if we want to look at post-merger retention and repeated mergers, we need to include that. So we include gravitational recoil in our post-processing method. So for any merger that N-Body 6 detects, we already have the masses based on N-Body 6 and BSE. So we take those masses, we assign them a spin magnitude based on some fitting formula from the MESA code. And then we assign a spin orientation, and then we plug it into this formula given by equation 1, which was developed by Van Meter et al. 2010. So this is essentially a fitting formula for gravitational recoil that is based on the post-Newtonian, based on numerical relativity, and also some post-Newtonian stuff helps them to get the form of the equation. I won't get into too much detail about the equation, but the important thing to know is that it depends on the mass ratio of the binary, the component spin orientations, and the component spin magnitudes. So, as I said, the masses are given by N-Body 6. The spin magnitudes, we use a fitting formula from MESA, and then the spin orientations, that's the last ingredient we need. Now, for black hole binaries that are formed dynamically, such as the ones we're talking about here in globular clusters, we expect that the the spin orientations are isotropic. So what we decided to do is, because these spin orientations do have a large impact on this recoil, instead of just picking one random orientation, drawing it isotropically and then done, what we do is we do it 10 to the 4 times, each time keeping the same spin magnitude and keeping the same black hole mass ratio, and just randomly assigning the spins. So, you know, heaps of different spins. And then we have this, and each of those 10 to the 4 iterations with different random spins will lead to a different gravitational recoil. So we can get a distribution of gravitational recoils.
Got it.
And then we can look at how many of those result in the second generation black hole being retained.
Got it. Cool.
And this is obviously it's not quite as good as actually doing it in the code, but it does allow us to turn the recoils essentially on and off, so that we can look at recoil, the merger chains with and without recoil. So now, to start with, we can talk about merger chains without recoil as a kind of a base case to see, so that we can compare when we turn recoil on. So to investigate merger chains without recoil, we'll focus specifically on the snowball case, because this was the one where we get the 7 mergers in a row. So snowball starts out as just a regular main sequence star, nothing particularly special about it. It goes supernova pretty quick because 58 solar masses is quite massive, quite short-lived, and it forms stellar mass black hole of 26 solar masses. And then it essentially migrates to the core quite quickly as through mass segregation, and as does all the other black holes, because they rapidly become the most massive bodies in the cluster. So you've got a lot of dynamical friction. They migrate to the core. So we get a dense core of all these black holes, which is where the fun starts, because then they can start interacting, forming binaries and doing some fun stuff.
Cool.
So once snowballs migrated to the core after around 11 million years, it then starts to experience a lot of these close interactions, and then rapidly forms a quite high eccentricity binary.
Sure. Mm-hmm.
It undergoes a few three-body interactions and then exchanges its companion for a different black hole, which ends up being the most massive black hole in the system, a 26.14 solar mass black hole. So now we have the two most massive black holes in a binary together in the center of the cluster.
Okay.
They then undergo multiple more exchange events until eventually forming the first merging pair. And this is actually something we see that's quite common, these constant exchange events. So then it merges, and then essentially this process repeats, because remember, this is without any recoil. So the second generation black hole, snowball, is retained. It's gained some mass from its merger. It then merges again and again. And if we go to figure 1, we can see the growth in snowball over the evolution of the cluster. So you can see it starts out, then merges again, and each time it's gaining some mass from this merger with the black holes that it's merging with. And one interesting thing to note is all of the black holes that merge with snowball, all of those low ones there, they're all first generation black holes.
Ooh, okay.
So every merger that occurs in this cluster is in this one chain here with snowball. There are no other mergers not shown in this diagram, which is interesting. So it kind of seems like snowball is suppressing any other mergers that are not involved with it. It kind of, because it becomes, after the first merger, since it's so massive, it dominates the dynamics of the core. So you can kind of think of it as the big bully in there. It's kicking out the other black holes that don't want to merge with it. So it is responsible for merging with all these black holes and also ejecting a lot of other black holes as well. So it's like the big bully of the cluster core, which is kind of interesting, I thought. And it is to be expected, since it's after the first merger, it's at least approximately twice as massive as any other black hole. Of course, it's going to dominate that core.
The rich get richer here. Yep.
Yeah, exactly. And this was, when we saw this, was very exciting, because 7 mergers, that's a lot, and also it gets to around 100 solar masses, which is the cutoff approximately for intermediate mass black hole. So this is a potential formation pathway for intermediate mass black holes. So as I said, though, that is without any recoil. So it's important to look at what happens now if we turn on recoil. So if we go down to the next section.
Okay. Ooh.
So we have more detail in here about the specific interactions. I will stop there actually on figure 3. So instead of going through too much detail, we can discuss figure 3. So this shows the period evolution and the eccentricity evolution of this snowball black hole.
Okay.
And these vertical black lines are indicating each of the 7 mergers. So you can see in the period evolution, starts off with a high period and then slowly decreases until it eventually gets close enough to emit a significant amount of gravitational waves, and then, orbital decay and then merger.
Got it.
And you'll also see those dotted green lines. Those actually represent exchange events where we have the binary and then a third black hole comes in, interacts, and kicks out one of the binary members and joins the new binary now.
Okay.
Now, most of the time, snowball is the one that stays in the binary and its companion is kicked out.
Yeah.
And this is because previous work has been done and they've found that essentially when you have these exchange events, it's more likely to kick out the lighter companion, which in this case will always be snowball's companion, because snowball's the most massive after its first merger. So most of the time, the snowball's companion is ejected and it has a new companion. So it switches partners a lot, essentially. And the last thing I'll point out here is in the eccentricity distribution plot, you see that overall the eccentricity is varying quite a lot.
Wow.
But the one part that I will point out is this highlighted red region.
Yes.
And that is because in that part, the binary is undergoing what are known as KL or quasi-Lidov oscillations. And this is where you have a tight inner binary, in this case, snowball and whatever its black hole companion is at the time. And you have a third body orbiting a distance. And essentially what that can do is drive the inner binary to extreme eccentricities. And that's what we see here, which is why it starts out at a lower eccentricity and then rapidly increases over time. And yeah, so it doesn't actually end up merging there, as we see. It's because essentially what happens is before it can drive it to a high enough eccentricity, that third body is actually ejected.
Yeah. Okay. Ejected or collision, yes.
So then we're left with just the tight inner binary that remains for the rest of the simulation and doesn't end up merging.
Got it.
So Snowball actually ends up in a binary by the end of it, but it just doesn't have enough time to merge.
Got it. Is this the only time that the Kozai mechanism is working here, or does it happen earlier?
As far as we can tell, it's the only extended time. It's hard to tell earlier because earlier in the simulation, there's a lot more black holes and it's a lot more chaotic. It becomes quite hard to tell if you're actually getting these KL oscillations or if it's just three-body interactions. But by the end there's not many black holes left, so it's
clear.
Things are a lot more constant, essentially, so it becomes more clear,
yeah.
So now let's go to section 4, and we can talk about what happens if we now turn on these merger recoils. So everything we've talked about just then, no recoil.
Recoil. Here we go, recoil. I'm with you.
So now if we turn on the recoil, what essentially happens is it prevents the formation of Snowball, which is a bit sad, but also interesting. So basically, if we look at figure 4, we can see now for Snowball, this figure is essentially representing the recoils velocities you would get from each merger in the chain of 7.
Okay.
And so the variation, each color of the histogram represents a different merger. And the reason why there's such a large range in recoil velocity for each merger is because of these spin orientations. Because we've locked in the mass ratios and we've locked in the spin magnitudes, but the spin orientations are changing. And that's why we do these 10 to the 4 calculations for each merger.
Right.
So this is just one example for this merger chain of 7, this Snowball merger chain. So you can see with merger 1, there is a decent proportion of the histogram that is in low enough kilometers per second to be retained by the cluster.
Okay.
But as you go to merger 2 and 3, there is a lower proportion at that low velocities. And then by the time you get to merger 4 in green, you'll see that the cutoff is above 100 kilometers per second, which is well above the escape velocity that we're talking about for our globular clusters. So in the cluster models that we're using, their escape velocities from center is about 25 kilometers per second. So well below this cutoff of around 130 or so. So basically, this shows why even with ideal orientation of our black hole spins, like you're still going to eject it and you can't get any more than 4 mergers because that product from that 4th merger will be ejected with a minimum of around 130 kilometers per second.
Yes.
So that's why we say these merger recoils prevent the Snowball chain from reaching 7. It does mean it could reach 4 mergers at most, but not 7. At least that's dependent on this specific merger chain. So it depends on the mass ratios and the and the spin magnitudes. But part of the reason why this we can't get any higher than 4 is because of the mass ratios. So you can see that over time, if in the top left panel, you can see that, as we go from merger 1 to 7, the mass ratios get lower and lower and lower. And as you get further away from unity, the recoils get higher, essentially.
Right.
So because Snowball is only merging with first generation black holes, it's getting more massive. The black holes it's merging with not getting massive. The mass ratio gets lower. So, and I'll talk about this a bit more later. One way you could get more longer merger chain is if you had multiple black hole mergers separately and then they merge together. So you have 2 second generation black holes merged together, because then they'll have approximately the same mass.
Right.
So the mass ratio will be closer to 1, and then you can potentially have a lower recoil. You still need good orientation of the spins, but, as we've seen here, it doesn't matter what your orientation of spins are. If your mass ratio is too low, you're getting kicked out.
You won't chain up. Yep, that makes total sense.
So unfortunately, our snowball merger chain doesn't happen if we're including these recoils. But that's good, because it tells us that our ability to turn them on and off shows us that exactly how it's preventing the merger chain from happening. So one cool thing we can do now is look at the merger chain statistics. So I've just been talking about this one snowball merger chain, but as I said, we did 58 simulations. We got a lot more mergers than the snowball chain. Let's look at the whole set of simulations, the whole set of mergers, and see what we can find and maybe make some statistical arguments about.
Okay.
So just stop there, and I'll just quickly define. We have, for the purposes of this section, we'll define merger chain length as L, and this L, merger chain length, is defined as how many mergers you have in the chain. So it's a pretty simple thing. So Snowball, it's got 7 mergers. It's got a chain length of 7.
Got it. Yes.
So if you look at the no recall case in table 1, we see we have 47 total chains, and we actually have one there with a merger chain of length of 7, that being Snowball, as we discussed. But also, interestingly, you can see that we have 4 other chains that reach a chain length of 4. So Snowball is still an outlier there, but we are getting some other longer merger chains than just 1. So a chain length of 1 would just be 2 black holes merge, and then that black hole just stays, doesn't merge again. It just sticks around or gets ejected, whatever, but it never merges again. Chain length of 2 would be, the 2 black holes merge, then that black hole sticks around and then merges with another black hole.
Another first generation black hole.
Yes.
Yeah.
And then if we look at, we did 2 separate instances here of recoil with no spin and recoil with spin. So with the no spin case, the only thing that affects the recoil is the mass ratio. And this is just saying, the point of this test was just to see, there is a chance that black holes don't have high spins. So let's just see what happens. Let's say they have no spin, just see as a base case. Snowball doesn't happen, but we still do have 3 length 4 merger chains. And now the more realistic case, because black holes probably have spin. So let's say we have recoil with spin, and we can see we don't get Snowball. And now, to get these numbers here in this last column, we just took the most likely recoil for each case. So if you remember before, I was saying we did 10 to the 4 calculations, each time different orientations of the spins.
Yes.
That leads to a most likely recoil. So if we take that most likely recoil for each merger, how many merger chains do we get? And that's what's in here, this 4th column. Sorry, the 4th column here. So almost all of the mergers are first generation.
Right.
We get 7 second generation and 1 third generation. And that's essentially the 3rd column. As I said, that represents the most likely outcome for all of our set of simulations and all the mergers. So pretty much all first generation 1 chain length 1 mergers, which It's a bit a bit annoying, but it's good to know because we can clearly see the effect of recoil. From turning it on and off, we can clearly see how recoil could impact it. Now, one thing we can do is try and see, do a bit of statistics and see, well, how likely is it that we could get a chain length longer than 3 there? Because that's the most likely option, as I said, to get only one chain length of 3. But there are other possibilities. So this is where figure 5 comes into it. So this is taking all the mergers across our 58 simulations. So there was 98, I think it was 98 mergers without recoil. Now let's take all of those and then we'll apply our recoils to them, doing the 10 to the 4 different orientations of the spin orientations. Let's see, take that whole set, 10 to the 4 times 98. Let's see how many merger chains we get and how likely. So you can see one option is almost all of them are essentially, so pretty much 100% are chain length of 1, as is expected. And then go below 1% of chains are chain length 2. Yeah. And then successively lower and lower, because the y-axis is, the vertical axis is on a log scale. So you see that by the time you get to a chain length of 4, although it is possible in our simulations, what you can read into this is that it is possible to get a chain length of 4 under based on just the simulations we did. You can do it. It's just very, very unlikely.
Right, you basically lose 2 orders of magnitude in percentage for every delta in the chain length.
Yeah, and this is actually, I mean, it's somewhat expected because these merger chains, they're like, even if forgetting about recoil, merger chains are multiplicative in nature, because in order to get a chain length of 2, you have already had to have had a chain length of 1 first. To get a chain length of 3, you have to have 1 and then 2. So they build successively on each other. So even without recoil, it makes sense that you would be less likely to form higher chain lengths. But obviously with recoil, they get even more unlikely.
More shorter. More unlikely. Right.
Yeah. But yeah, it is possible to get a chain length of 4, which is still, that's pretty cool. It's just hard. You got to get everything perfect, essentially. I will point out, though, that this is specific to our simulations and our mergers, because, as I said, the mass ratio does make a big difference. So, and our mass ratios are set through N-body 6 and through the mergers that happen in there. If you had some mergers with different mass ratios, this graph would look different, obviously. Yeah, but this is just something that it is possible to get a chain length of 4. Very cool. And what we can do now is actually essentially get an order of magnitude estimate for how likely snowball is based on table 1 and figure 5. So we go down to next equation. I believe it is equation 6. Yes. So yeah, basically, this is by no means a proper rigorous calculation. It's just an order of magnitude estimate to see how likely a snowball-like event could be. And let's maybe compare that to the LIGO-Virgo event of GW 1905-21. So in equation 6 here, we've got 4 variables on the right there. So R star is just the co-moving star formation rate at a specific characteristic time. And then we have F sub GC, which is our estimate for the fraction of star formation that is occurring within globular clusters of comparable size to our model. We take it to be about 10 to the negative 3. F snowball is the fraction of those star clusters that are likely to produce a snowball merger chain, which we can estimate F snowball based on our simulations. That will depend on if we say no recoil, recoil without spin, or recoil with spin, which I'll get into in a second. And then lastly, we've got M sub GC, which is the characteristic mass of the star clusters that we're modeling, which for our models we use is about 6.5 times 10 to the 4 solar masses.
Okay.
So this would change if you have, essentially if you're looking at heavier star clusters.
Right.
However, if you have heavier star clusters, then the star formation rate might be a bit lower because the heavier star clusters are less common than the ones that we're looking at. So the star clusters in our models, the models of star clusters we're using are median mass star clusters. So they're essentially middle of the road star clusters. And we can estimate R star to be about 0.1 solar masses per year per megaparsec cubed,
Okay.
which corresponds to the co-moving star formation rate at a redshift of 1.2.
Okay.
And
yeah,
we're also neglecting a cluster birth mass function just because, you could do a more complicated calculation with it, but for the purposes of this, we're just doing an order of magnitude estimate. Yep. So if we take what I just said, and then we just need to calculate F snowball, we can calculate F snowball here in the top right of the screen to be 2.3 times 10 to the negative 12.
Okay.
And that's taken, as you see there, based on how many snowball merger chains we get within our simulations.
Okay.
And then we get a formation rate of 3.5 times 10 to the negative 12 per gigaparsec cube per year.
Okay.
Small number.
You're very. Okay.
So that is with spin and with recoil. So this is well below the estimate LIGO gave for GW 1905-21 LIGO fence.
Okay.
If we turn recoil off, the much more preferable case, if you scroll up to equation 7, we get 0.03 per gigaparsec cube per year. And this is actually within the 90% confidence interval for LIGO's estimate for GW 1905-21.
Wow.
But that, as I said, that's without recoil. So let's say there's a very, the understanding of recoil is still not complete yet. There is a chance that we're completely wrong about it, and the black holes aren't getting recoil. So then this could be a very viable thing that would match up with 1905-21. But the much more likely case is that our understanding of recoil is pretty good. Some very smart people doing numerical relativity have come up with all these formulas. They're probably within 1% accuracy of what's actually going on, in which case our snowball formation scenario doesn't explain the rates that LIGO has estimated.
Right. Okay.
And this is expected because, as we saw before, including the recoil makes it pretty much impossible to get these higher merger chains. It makes it so unlikely. So finally, a quick little discussion. As I said, these recoil chains are very dependent on, the merger chains are very dependent on the recoil, particularly including the spins, which basically prevent higher order chains. However, even if we take our most likely recoil case, which was given in the last column of the table 2, you saw that there was still one 3-length chain.
Yes.
Now, that was essentially the most likely scenario. That could be a potential explanation for 1905-21, because you could get, if you have a chain length of 3, remember, means you have 3 mergers in the chain. What could happen is you could have 4 first-generation black holes, they merge. Now you have 2 second-generation black holes that merge. That could explain GW 1905-21, because those 2 second-generation black holes would be the companion black holes that merge in 1905-21. And since those are both second-generation black holes, that would explain why they're above the mass gap, because they didn't form through core collapse, they formed through a previous merger of first-generation black holes. And the fact that we see this chain length 3 in our most likely scenario is a good indication that getting these chain lengths of 3 is actually a reasonable scenario. And again, that's with 58 simulations. If we had 1,000 simulations, that would probably have more of these chain length 3s. So yeah, one of the limitations is the number of simulations we've had, obviously. And yeah, essentially, yeah, that's one thing I'll say is taking all these simulations, on average, the last simulation with a chain length above 1 occurs at around 4.7 gigayears.
Okay.
Which would indicate that these hierarchical or repeated mergers are happening in young globular clusters, so below around 6 gigayears. And this is most likely because in those early days of the globular clusters, there's much more black holes in the globular clusters, because as they age, the black holes interact and eject each other, the population evaporates over time.
Yep.
So it makes sense that you would want these to be merging in these earlier clusters.
Yeah.
Yeah. And one thing that could mean is that we would potentially see more of these as LIGO's volume that it can observe increases, because further out we can see, the younger the clusters that we're going to observe, potentially see more of these hierarchical mergers. So yeah, in conclusion, recoil is a massive impact, has a massive impact on these mergers and the merger chains. It does prevent our Snowball 7 chain from happening, but we still do see the presence of some 3 and 4 chains, and they could explain 1905-21. They don't quite have the rates, but again, that's dependent on our specific simulations. So it could be a possible formation scenario for 1905-21.
Very cool. Very cool. Very nice. Nice work. Oliver, thank you so much for walking us through this very awesome APJ article. Thanks.
Thank you for letting me.
Yeah, and you touched on it a little bit there at the end. Or you a couple times as we went through. So let me ask, where do we go over the next couple of years on this topic? You mentioned only having 58, but what if you did have 1,000, or what if you had 10,000, or what if you went to 10 to the 6 particles in the direct N body? Is there some observational evidence that we can get a handle on, either electromagnetic or gravitational in some of the available clusters? So where do we go?
Yeah, well, that's a really good question. And yeah, I kind of touched on that a bit. So some of the next work I want to do is, in fact, I'm currently doing as we speak, is running a big new set of simulations. So we're limited by computational resources and all that with how many simulations we can run, obviously. But we want to run at least over 100 simulations. So at least twice as many as we had before. The other thing we're doing with our new simulations is I've upgraded the N-body code to include gravitational recoil on the fly. So it's calculating it in the simulations as opposed to us doing it in post-processing. We can still do our post-processing method of, different orientations of spin as well, because I'm still saving the outcomes of these mergers. And then so we can re-say how likely was it that would be retained instead of ejected. But having it done in the code is a bit more preferential, because it means that if a black hole is meant to be ejected, it will be ejected. Whereas in post-processing, if we find that it should have been ejected, well, it's still in the cluster, unfortunately, because the simulation didn't know. Yeah.
Right. Well, that'll be a good verification between those two, right? How good is the post-processing approximation versus putting it in? So yeah,
that'll be really interesting to see. The other thing I'm doing is, as you touched, well, what if we run larger simulations? That's very dependent on how long it takes to run these simulations. So I'm actually working with one of my colleagues in Japan, Kaigo Nitadori, to help upgrade the GPU implementation in N-body 6 to speed it up, which will make it more feasible to run larger simulations. People also do Monte Carlo simulations, which you can run much larger clusters because they're not as computationally intensive. But it's nice to be able to compare between N-body and Monte Carlo.
Indeed.
N-body also has certain advantages. I won't go into those now, but the other thing is in the next few years, LIGO is only getting more powerful. Virgo is getting more powerful. Cagra is coming online.
Yeah.
The fourth observational run for the LVK system starts like it was. I think it was next month.
I think it's
It's
next month.
very
Yeah.
assuming it hasn't been delayed. I think it's next month. So, and there's been upgrades since '03, and also with Cagra being online as well, at least at the start, we're going to get a lot more mergers, and more mergers means more data, which means our information increases, and then that'll inform essentially what we want to do. Who's to say we don't see a few more 1905-21 like events in '04? Because if we do, if it turns out they're more common,
Yes.
then we need to, then we really need to start thinking hard about what can be producing so many of these.
Yeah.
Because maybe we do have to change our understanding of core collapse physics. Who's to say?
Fair enough.
So yeah, there's a lot of exciting things coming in the future.
Cool. Very nice. Well, I look forward to the upper mass gap and mergers. It's a great topic. It's a hot topic. I really look forward to seeing it advance over the next couple of years. And I think it'll probably give you a very awesome PhD thesis. So awesome. Thank you so much for Oliver, for walking us through. Nice.
Thank you for having me.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Yeah.